let's pick up on the last thing that we did, which was this big mess. I don't know, you guys want to start from here or you want to start from scratch again? Scratch. All right, well, from scratch. We have a surface integral, so it's a double integral over a surface, not just a regular plain double integral, but it's actually over a surface and the ds. So there's a couple of clues that would make you think that this is not a regular double integral, but rather it's a surface integral. So the surface S is described to be the boundary of the region enclosed by some three-dimensional solid here. And it looks like we have three solids, or three surfaces, that we have to compute this triple integral over. So we have a cylinder, we have the x is equal to 0 plane, and then we have this other plane that cuts the cylinder. So each of these would represent a surface, and I would probably want to call these surfaces S sub whatever, and I think I ended up calling this surface S sub 1, and then this surface, the cylinder itself, is S sub 2, and then the other plane is S sub 3. So what we want to do is we want to focus on each of those surfaces, because what's going to happen is that our surface integral is going to be broken up to three surfaces. This is xz. And then we would have to compute each of these surfaces separately. Which means for each of these surfaces, we would parameterize them. And then once we get our parameterization, we would put it into their respective integrals and then figure out limits for the parameterization and then work from there. Okay? So let's take a look at the first one, S1, and see how we're going to parameterize that. This is x is equal to 0. But it's going to be within the cylinder. So if you were to draw this, it's just going to be that disk on the YZ plane, where x is equal to 0. So, by the way, since x is equal to 0, when we put it into this integral, it's going to be 0. So we don't really need to do any work with this because it's not going to contribute anything. But let's go through a little bit of the process of parameterizing this. And the way I would parameterize this is just like with a regular graph parameterization, or I think I call it graph parameterization. Your R vector is going to have a 0 for the x value, and then you have y and z where y squared plus z squared is less than or equal to 7. I think this has radius 7. And with this, when I set up the integral, I probably want to go polar to do the computation for this. But like I said, when you do this integral, you're going to have 0 for x and that's going to make the whole integral equal to 0. So I don't think we need to bother with this problem anymore because it's not going to have any contributions. Okay? All right, so we're done with that. Now let's take a look at our second surface, S2, and that surface is the cylinder. The thing about this particular cylinder is that it has it's being cut at some angle over here, so it's not a completely flat cylinder. So that's going to make this a little tricky for us. And the parameterization for this is going to be tricky as well. It turns out that to parameterize a cylinder, we can do this in cylindrical coordinates. And remember that we're moving along the x, right? So we can move along the x in the x direction. So what we're doing here in terms of cylindrical coordinates is looking at it sideways. You know how cylindrical coordinates we had x equal to r cosine theta, y is equal to r sine theta, and then z is equal to z. So this is like your z is equal to z. And then the x and the y, or what used to be x and y, is really y and z. Okay. So this is how we would think about cylindrical coordinates that's sideways. All right? Does that idea make sense? So now we already have one variable z. Remember cylindrical coordinates, like spherical coordinates, they describe a solid with the 3 parameters. So we had r, theta, and z, or in this case we have r, theta, and x. Now, if we have 3 parameters like this, we are actually looking at a solid. So what we're going to do is we're going to look at this a little bit carefully and say one parameter is actually constant. Which parameter is constant? So I'm thinking x is not constant because I already have it written down here. So r or theta, if I'm looking at the surface, r or theta is constant. Which one do you think is constant? R. What's r equal to in this scenario? R is the radius of the cylinder, right? And we're not filling in the cylinder, we're just looking at the surface of the cylinder. So with r equal to 7, in our problem, that's going to make it so that we only have two parameters, x and theta. So r is constant. And then if we plop down the x and or the y and the z values here, which is 7 cosine theta, 7 sine theta, then we really just have now a surface because it has two parameters, x, and it has theta. Right? So the question is limits. We want a domain for this to describe our domain, and our domain is going to be an x and a theta. So let's figure out our x and theta limits. Theta, I think it's easy. What's theta go from? It goes from 0 to 2 pi. It goes all the way around because you're looking at the whole cylinder in terms of its circular part, right? If for some reason you only took the top half of the cylinder, then your limits will change. But since we're going all the way to 2 pi, then your theta is going to be from 0 to 2 pi. How about your x? Your x values go from, I'll say that they go from 0, but how far do they go? So they go up to this plane. That's where it gets tricky. They go up to this plane, right? And so the x value here would be 9 minus y. But this still isn't quite good enough because we said that our values were going to be x and theta. I don't have any y's in my parameterization. So what do I need to change? So according to what we have here, y is equal to r cosine theta, or 7 cosine theta. So this would be 9 minus 7 cosine theta. So that would be your y limits, or your x limits, sorry. So if I were to write this integral, this surface integral here, so integral S2 xy ds, or xz ds, this is going to turn into a regular double integral over a flat domain. My flat domain goes from, it's x and theta. So if I look at my parameterization, I replace all my x's with x. I don't have any y's to replace, but if I did, I would have put in 7 cosine theta for that. But I do have a z. I would replace that with 7 sine theta. This is a z. This is a 7. Okay? And then I'll say I want to integrate with respect to x first. dx, my x goes from 0 what? 9 minus 7 cosine theta. And my d theta goes from 0 to 2 pi. Are you guys taking notes in pencil? Good, because I forgot something. What did I forget? R? 7? Something, right? What? Another x? No. I think I forgot a 7. But we don't want to just say 7. So technically, remember how this works out, the ds? What does the ds represent? Well, it depends on how you do your parameterization. So there's this whole piece missing here, this ds, needs to get replaced with this. And what goes here? It's kind of like the Jacobian, but from the ds, it's the magnitude of r sub x cross r sub theta. Remember that? So, without doing much work, I could tell you that this is r vector, the r vector. This is going to be 7, just because of when you take the derivative with respect to x and with respect to theta. Is it going to be 7? Well, we better do it, just in case it's not equal to 7. R sub x is 1, 0, 0, because there's no x's in those. R sub theta is 0, negative 7 sine theta, positive 7 cosine theta. So if you do the cross product, Rx by R theta, with respect to theta, 0, 0, so that's gone. With respect to the middle term, the j component, it would be a negative 7 cosine theta. And with respect to the k component, it'll be negative 7 sine theta. So the magnitude is going to be the square of each of them, 49 cosine squared plus 49 sine squared. So, yeah, it does turn out to be 7. Okay. So here's one integral that we have to compute. That looks like an easy enough integral to compute. I already did it. It's equal to 0. Okay. All right, so that takes care of that. Now we have one more surface to look at, and the last surface is S3. Let's take a look at S3 again. S3 is this purple. I think we use red for that one. So S3 is this little bit of a circle, kind of like an ellipse, I guess. That plane, x plus y is equal to 9. That's within the cylinder. So this has a shadow of on the xy, on the yz plane that looks like a circle like this. So I think we can take advantage of that. So we can just say that this is really just a plane whose shadow is a circle on the xy plane. So how can we parameterize this? We'll parameterize it by saying r is equal to, so we'll just use the plane x and y. So we'll say this is a function of x and y. So we'll have x here and then y here. No, sorry. I think we want y and z. So x is equal to 9 minus y. Because this thing has a shadow on the yz plane, I want to kind of keep my variable at y and z. And the shadow that this has is going to be my domain. So my domain is going to be y squared plus z squared is less than or equal to 7. So it's basically a shadow. So just like the S1, which we didn't really do, but just like the S1, we want to look at this as we're going to go polar with this integral. Well, let me set it up first without going polar yet. So this integral is going to be double integral of x and z dx or dy and dz. And so instead of saying my yz business over here, I'm going to call this d temporarily because I have to try to describe the circle. And instead of putting, minus square root of, what is it, 49 minus z squared or y squared, I'm going to leave that blank for now. And remember, when you change the ds into a dx dy or dy dz in this case, we need to find the cross product business. Okay, so let's take a look at ry. R sub y would be -1, 1, 0. R sub z would be 0, 0, 1. And we want to cross that and take the magnitude. So ry cross rz is equal to I got 1 -1 0. I'm more concerned about the magnitude, so it looks like the magnitude is square root of 2. So I have a constant square root of 2 sitting out there. Okay? So since my domain here is a circle, I'm going to go into the polar coordinates. And I'm going to let my y equal to r cosine theta, let my z equal to r sine theta. So I have 9 minus r cosine theta times z r sine theta. I have a square root of 2 that came from the cross product. And then now, since I'm changing into polar, I'm going to have an extra r here. dr d theta. And a circle of radius 7 gives me an r limit going from 0 to 7, and theta gives me theta limits from 0 to 2 pi. Okay? Man, this is not the right problem to start with. So, I did this in Wolfram Alpha as well, and I got 0. Okay. So that's it. So I did work on this graph to try to see if I can get a good look at it. And the tricky part about graphing programs, especially with something like this, is that when you're combining graphs and you're using u's and v's for your parameterization, a lot of times my limits for my parameterization, if you look at these limits, they're functions, and they're this one, the limits happen to be a circle, comes from a circle. And so what I had to do is I needed to change the way I thought about limits, because these programs can only do constant limits. So limits for my parameters go from 0 to 1. So if I were to try to parameterize this circle all the way at the bottom, that's a circle of radius 7. Instead of my u going from 0 to 7, like my r would normally, I would just multiply this by a factor of 7. And instead of my theta going from 0 to 2 pi, I'm going to have my theta go from 0 to 2 pi, but I'm going to multiply my v with a factor of 2 pi. So by doing this, I get to get that circle. See that circle? It's there now. Well, let's get rid of the other graphs. So here's that circle. So the next thing I wanted to do is I wanted to draw the cylinder. And again, trying to keep my limits from 0 to 1 the whole time. The cylinder came about by looking at x is equal to x, or how did we put it? Where's the cylinder? Right here. X is equal to x, and then y is equal to 7 cosine theta, and then z is equal to 7 sine theta. So that's what I did over here. I think that's what I did. Nope, that's the other one. But the difficult part here is that I couldn't just let x equal to x, because if I let x equal to x, which in this case would be u, and if I were to graph this, I would get a really thin cylinder. So I needed to multiply this by a factor of something that's dependent on how high it's going to go, or how far it's going to go. So I needed to multiply this by the function 9 minus y, and then add to, because I'm dealing with only two variables, I need to replace the y with what y was equal to, which is 7 cosine. So there, now I have this part of the cylinder that comes out that gets cut off. And then the last part was the top of this thing. So that gives me the solid, the three sides, or the three boundaries for that solid. Okay?
Now, since we're integrating with the solid as bounds,
Yeah.
then the answer, the integral represents surface area.
No. If this function in here was 1, then it would be a surface area. What we can assume is that this is some sort of density, or because our answer is 0, it's hard to think about it that as density. So we can assume that it's like the temperature. So this is the temperature on this surface. And so what we want by doing the surface integral is we're finding the average temperature over the whole surface. So it turns out that maybe some of the temperatures in the surface is positive, some of it's negative, so it all just kind of cancels out, and the average temperature is 0. So that could be one way to look at it. But it's not a surface area. If you did make this equal to 1, then it would be a surface area. Okay? All right, so I don't think I ever put the formal definition of a surface area, aside from giving you a bunch of examples last time. So let me just summarize what the surface area is or does, or how to use a surface area. Let's call it surface integrals. And the surface integral in general looks like this. It looks like a double integral, but then when you see what goes down here, it's an S. S stands for surface. And you have a function. And then the D differential is the surface, ds. And notice it's capital S, not the little s. The little s stands for curves. These things stand for surfaces. So what we want to do is we want to parameterize S, just like we parameterize the curve C, with a parameterization R of two variables, U and V. And then what's going to happen is that this is going to be X of U and V, Y of U and V, and Z of U and V. Now these are all functions of U and V, just like we had R cosine theta, R sine theta, and whatever. And so this is going to become, oh, by the way, this is the parameterization, but when you parameterize, U and V have to end up in some domain, two-dimensional domain. So this is how it's going to work now. It's going to become a double integral, and I want to keep stressing the fact that a double integral and a surface integral are different in nature. A double integral is flat on the xy plane. A surface integral is a surface on a three-dimensional space. So our f is going to get bombarded with the parameterization. So eventually our f that used to be a function of x, y, z is now going to become a function of u and v. So that's your f. And now your ds is going to get multiplied by the surface area element. So the f and the ds get changed into that, and where dA is equal to du dv or dv du. And D is our two-dimensional domain. Okay? So this is a surface area, or surface integral. So that's kind of like what we did. What I was doing is I was replacing x and z. That was the integrand. I was replacing it by components of the parameterization. And then my domain was a domain. If it was a circle, I probably wanted to transform into polar coordinates. And then I always had to compute this, which for the problems that we did happened to be constants, which was nice. But it's not always going to be like that. Okay? All right, we have one more integral to go, one more type of integral to go. But before we do that, let's try to recap all the integrals that we know. We've kind of talked about a few integrals already and see if we can try to find parallels to them. How did I put my integral list before? All right, let's see if I can make a chart. I'll start off with a regular integral from Calc 1 and 2. This is kind of like a regular integral. And in general, whatever integral we have, we want to basically break it down and make it look like this. And actually, what I want to do is I kind of want to rewrite this integral where you have the interval a to b. You can just write it as I f dx. That's a plain old single integral. And then from here we went to a double integral. Where we're integrating over a two-dimensional region. And then after that, we did a triple integral. Where we were integrating over a solid. So the key differences between this is, well, it's 1, 2 versus 3. It's a one-dimensional region that you're integrating over, interval. Versus a 2D region versus a 3D solid. And you can see the D, if it's just a one variable x, or if it's a capital A, we know it's with respect to an area element, or a capital V with respect to a volume element. So this is what we know of as a double integral and the triple integral. Okay? All right. So somebody said, well, if we're going to integrate over a one-dimensional interval, let's generalize the interval into a curve. And hell, we can integrate over a one-dimensional curve, right? So it turns out that we've done that. We integrated over a curve, and this is a one-dimensional integral, so we just have one integral. This is a curve, and the curve is one-dimensional, and so you have a single integral. Do you remember what we called this? What kind of integral we call this? We call this a path integral. And then just right now, we just talked about integrating over a surface. Oh, I'm sorry. The path integral doesn't have an x. What should it have? Do you remember? R. We've been using S. I've been using S at least. I think the book uses R. I think R would have been better. And then our surface integral is a capital S instead of a little s. Surface integral, where S is a surface. And if you look at a surface is really a two-dimensional object, right? It's infinitely thin. We're just looking at the surface, and so there's no thickness to it. It's not a volume. This is still a 2D object, which is why we're dealing with it as a double integral. And then if you remember, in terms of computing this, we tend to change the ds into something. We change the ds into something for the surface integral. And so if you remember what ds is equal to, it's based on the parameterization. It's the magnitude of r prime of t dt. And so now we get to integrate it like it was a regular dt dx integral. And your ds here, based on your parameterization, is equal to the magnitude of the cross product of the partials. And I was going to put dA there, but I'll put du dv to say, well, it's just a combination of those. Okay? Well, it turns out that there's no triple integral equivalent to this. We did talk about one other integral. Do you remember what the other integral is that we talked about? A line integral. So a line integral is a single integral over a curve of not just a regular function now, but an actual vector field. And so when we write this out, we have a vector field, and we can't integrate a vector field, and so what we do is we integrate by the tangent element vector. So we're still looking at a one-dimensional curve. So to make our connection here, our ds is r prime of t dt without the magnitude, because we need to dot it with the vector field. Now, because we lose the magnitude, it does make a difference whether we're going from one way, from one direction to the other, or vice versa, right? So orientation is important here. Orientation matters. For this integral, line integral over a one-dimensional curve of a vector field. So the last integral that we're going to talk about would fall in this category right here. So just based on this chart, what do you think this is going to look like? So it'll be a double integral over what? Over C. C is a curve. C is a one-dimensional object. Probably over a surface. So this is going to be over a surface, S. Now what's going to go inside? What's our integrand? But what goes in here? Little f? Big F? Big F with an arrow on top, so it's a vector field. So now we're going to do a surface integral over a vector field. And so, and this one is what? D, capital S. Just capital S? Capital S with an arrow on top. You know what this integral is called? This is a flux integral. Cool name, huh? Flux capacitor comes to mind, yeah. If you're integrating over a capacitor, I'm sure you can call it a flux capacitor.
So would that represent the amount of whatever passing through the surface?
Yeah, yeah. So
if
it.
you have like a net in pond,
Yeah.
how much water is either entering or exiting?
Right. Yeah, let's use that example. Let's finish this off first. This is a 2D surface. And now let's compensate for our ds, capital S over here. And look at the d little s for both the path and the line integrals. D capital S, what do you think this will end up being? Without the magnitude this time. So it's the actual cross product which gives us a vector, and now we're going to be able to dot that with this vector. By the way, I didn't really talk about this too much. When you cross those two tangent vectors, what do you get? Do you know? With respect to the surface. I should have talked about it when we were talking about the surface. What? The what? Normal vector. So this turns out to be the normal vector. And so sometimes you'll see the flux integral written a little bit differently. You might see the flux integral with a dot n, ds, ds without a thing. So sometimes you might see the flux written as a double integral of s of f dot n ds with no arrow on top. So this is another common way to write the flux integral. It's a surface integral but they compensate with that dn, the n. This little n technically is a unit normal component. So if you look at the unit normal, you can think about this thing divided by its magnitude, and you'll see how things will cross out and cancel out, and then everything will be nice and neat. Okay, so that's the flux. Okay, now that we know that that's a flux integral, we should probably do an example or something. Yeah, let's do an example. There's more about integrals that I want to talk about, but we'll see if we can squeeze that conversation in a little bit later. So they put this in the same section, the surface integral and the flux integral. Why is this blocked out? I don't know. I understand what that is. Oh, there it goes. So, did I write orientation is important? Okay. So it turns out that the orientation is important only to change the signs. So if we think about a vector field, I didn't really expand on this idea of a flux, or what a flux is. You know, Lauren just talked about a fishnet. Do you guys understand that example, more or less? So it's like, let's see if we could do a little sidebar here. If you have a fishnet, and then you're lifting, you're getting this net, and you're lifting it up. And so the fishnet has normal vectors that go out this way. And what happens when you lift it up, you can imagine the field for the water pointing straight down because of gravity. And so you're looking at, more or less, you're looking at the work that's being done by the water when you pull the net up. I don't know if that makes sense. And so you're really taking a bunch of dot products, and so that's the dot product that's involved in the flux. It makes a little bit more sense when we talk about magnetic fields and gravitational fields and things like that. All right, so that's the general idea. And if the orientation is going outward or going inward, it does make a difference. And so let's do this problem and see if we could talk about orientation a different time. All right, evaluate this surface integral. They call it a surface integral, but since this is an f dot ds, it's really looking at the flux. Oriented, in other words, find the flux of f across s for the closed surfaces. Oh, this is more than one surface again. Oh, this is just one surface. So the surface is z is equal to this thing with limits on the boundary. So if you're looking at like the xy plane, we're going to go x goes from 0 to 1, y goes from 0 to 4. And then your surface is up here somewhere. I don't know exactly how it looks like. let's say your surface looks like this, and I'm not counting the sides, I'm just counting this. I'm just counting this part as my surface. Okay? And then you have a vector field, whatever that vector field looks like on this three-dimensional space. It's going to be passing through that surface, and so we're wanted to know the flux that goes across that surface. All right, so according to our formula, we want to parameterize the surface, and to parameterize the surface, I probably want to go with just the XY parameterization. I think I called it the graph parameterization, where x is equal to x, y is equal to y, and then z is equal to x times e to the y. So that's our parameterization. And then we want the cross product, Rx cross Ry. So we've seen this before. Do you remember? It's like the gradient, but negative, and then a positive one at the end. Okay. So in case you don't remember, it goes something like this. The Rx vector, I'm going to put that in the middle vector. It's 1, 0, and then the derivative with respect to x. The Ry vector goes in the last row. That's 0, 1, and then x e to the y. And then we pretend you have I, j, k, so that when we cross it, we're going to get a vector. So when we cross it, we get a negative e to the y. We cross out the middle, we get a negative x e to the x. So this is basically the gradient, two-dimensional, right? And then the last component just happens to be positive 1. So this is our normal vector. If we were to draw this normal vector on this surface, one of the clues that I have for this normal vector is that this normal vector is positive in the z direction. So based on my drawing, it's inaccurate, but say the graph kind of looks like this. Based on my drawing, I would probably say that my normal vector has a positive z component, so it's going to be going upward. So this has an upward orientation. And if I look at the problem, that's exactly the orientation that I want. So maybe I got lucky there. But if you have a different orientation from what they have, what they want versus what you have, then your answer is going to be exactly the same, except it's negative. Okay, so based on what they have, I would call this an orientation preserving parameterization. Okay? That's kind of long-winded. What should we call it? How about just OPP? Down with OPP?
Yeah.
Or is that too old?
No,
You down with OPP?
yeah.
Yeah. What? OPP. OPP means we're keeping the parameterization. Parameterization preserves the orientation. Orientation preserving parameterization.
What's the meaning of the hood?
If it goes the other way,
No, the hood.
oh. If it's going the other way, it's called ORP, orientation reversing parameterization. It means you're going backwards. All that means is that if you have an OPP, your answer is going to be your answer. If you have an ORP, then your answer is going to be negative. All right, let's get to this. Our f is equal to this thing. So I basically want to put my parameterization in there. So x is x, y is y. And z is not z anymore. Z is going to be x e to the y. Okay? So now I take my f and I dot it with my ds. My ds, remember, this normal vector plays a part in my ds. So I'll take xy 16 x squared, and I'll rewrite this as xy e to the y. I want to dot that with negative e to the y, negative x e to the y, and positive 1. So I have xy e to the y negative minus 16 x squared x to the third e to the y, and plus xy e to the y. It looks like e to the y, xy e to the y would cancel, and I have, looks like I'm going to have a negative 16 x cubed e to the y. Okay, so that's my surface, and this is my parameterization. So I make this into a surface integral. The integral of f dot ds, I guess I should put two integrals here, is equal to a double integral now of negative 16 x cubed e to the y, and I'll go dx dy because my limits are constants given in the problem here. My x goes from 0 to 1, my y goes from 0 to 4, and now this is just a plain old double integral that we should be able to solve. Okay? All right, we've semi-successfully completed a flux integral now. Is that the answer? All right, so remember, if your orientation was reversing, then whatever answer you get, just throw a negative sign. But what we're doing is we're basically trimming this down to a surface integral and then down to a double integral. Lauren?
If it was an ORP, would we have a negative 1 in the dx vector?
No, we would throw in a negative. If it's an ORP, we would throw in the negative at the end of the integral. So regardless of what this is, positive or negative, in any of these things, that just means that this is totally opposite from what we want to go. Yeah, wait, ask your question again. If this was ORP.
So if that was an ORP, then shouldn't that answer vector be negative e to the y minus, or comma, negative x e to the y, comma, negative 1? Would that?
No, it would be positive. The whole thing would be negative. So you would change the signs for all three components. So if this was ORP, you can go ahead and change all these signs to negative, and then pretend it's OPP. All right. In this case, because it's up to what they want. The problem wants an upward orientation. So if they wanted a downward orientation, then this would have been ORP. Right? So based on their needs, what they give you, what they want, versus the parameterization that you came up with. Okay? All right. Work on your labs. Maybe it'll help a little bit. Maybe.